Steve's just building up the tension at the moment.
Leave me alone.
Okay, and finally, our second keynote talk on, well, is it sun or stellar? Maybe both. Dynamos is Steve Tobias from Leeds. And you've got 5 minutes extra time.
Oh, well, there you go. See if we can get us to tea 5 minutes early. So I'd like to thank the organisers again. I'm not really meant to be here. It was originally meant to be Paul Charbonneau who was talking, so I'll try and do my best to fill in for him. And what I'm hoping to talk a little bit about today is the theory for solar and stellar dynamos, and to, at least for the geophysicists, explain why are we still arguing about this, and also Hannah gave a beautiful talk, but why are we still drawing cartoons of the solar dynamo? I mean, we're still really drawing cartoons, so why are we doing this? Okay, so I will go very quickly through this. What are we trying to explain? Some observations of the solar cycle. Hannah's done most of it. I'll point to a few extra observations. Observations of the flows, I'm really not an expert, so I'll be even more brief. And I'll talk about why is the problem hard, the solar dynamo problem hard, and it's hard in a different way to the geodynamo problem. So this talk is really aimed at you geodynamo people. And what are the modelling strategies we have? And then I'll talk about, we are drawing cartoons, so what are the cartoons for solar dynamo action? And I'll talk about the pros and cons. So those of you who listened to Hannah's talk may have thought, hang on a minute. There's something wrong with this model for the solar dynamo. And there is quite a lot wrong with that model for the solar dynamo. The trouble is, there's quite a lot wrong with all of these models for the solar dynamo. So you just have to pick your favourite one and stick with it. Or you can change your mind, I guess. Up to you. Okay, my usual advert here for if you're interested in solar and stellar dynamos. I got most of this talk from this paper here, from one by Sasha and Matt. When Matt asked me to give this talk, I just asked him why he wasn't giving it, and he didn't really have a very good excuse, so except he didn't really want to. There's some nice reviews of dynamos here, and of course, there's the famous book, which you can see outside, that Emmanuel will sign for you, and Keith will sign for you if you tip him 10 quid, I think it is, going right. Okay, so I'll be very quick. So Hannah showed the solar cycle. Here we have a magnetogram of the solar surface. You can see, as we open it out, we have active regions with blue and yellow in the southern hemisphere and yellow and blue in the northern hemisphere. And these waves of activity are going to migrate from mid-latitudes towards the equator, die out, and come back again at mid-latitudes with a reverse polarity, migrate towards the equator, die out again. Here we go, dying out. Come back at mid-latitudes, migrate towards the equator, and die out again. So that's three activity cycles, or 1.5 magnetic cycles that we have there. Okay, we don't need to do it again. And Hannah showed this, the butterfly diagram, where the waves of activity migrate from mid-latitudes to the equator. We have, this goes back to the late 19th century. You can see on this time scale, actually the activity seems to be fairly constant. That's not quite true. Hannah talked about Hale's polarity law and Joy's law, so I don't need to say too much about this, and that the polarity of the magnetic field reverses every 11 years, hence we have a 22-year magnetic cycle. But if we go further back, so Hannah showed essentially this one here. This is the sunspot number going up and down, the nice 11-year cycle. The modulation on the longer time scale that we have here, the so-called Maunder minimum. And then Galileo was doing his observations over here. This is from a very nice paper with some very beautiful diagrams in here in Nature Astronomy. You can see the butterfly diagram. You can see it waxing and waning. So in relation to Bruce's talk this morning, there's a question as to whether this modulation of the basic cycle is deterministic or stochastic. We could have a long discussion about that. That's what I did my PhD on a long time ago. You can see some other interesting things, that when the sun emerged from the Maunder minimum, most of the sunspots, or in fact all of the sunspots pretty much, were in the southern hemisphere. So there seems to be a roughly symmetric dipolar field. when you emerge from the Maunder minimum, you have a hemispherical dynamo, if you like, so a quadrupole and dipolar contribution. And there are times where you see sunspots at the equator, here, 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 which indicates that there may have been a significant quadrupolar component. Okay. So that's something to bear in mind. Well, Hannah talked about this. The solar cycle is not just visible in sunspots, in the polar field as well. The solar corona is also modified as the cycle progresses. And it's important to realize that the polar field reverses every 11 years, but out of phase with the sunspot field. So it's really a global magnetic field reversal. Okay, so Hannah didn't talk about proxy data, which I think is quite important for us to understand what's going on. So the sun's magnetic field modulates the amount of extragalactic cosmic rays hitting the Earth's atmosphere, and those are the cosmic rays which are responsible for the production of some of the terrestrial isotopes, such as beryllium-10 and carbon-14. So beryllium-10 is stored in ice cores after 2 years in the atmosphere, and so in beryllium-10 we can see the 11-year cycle because the 2 years is shorter than 11 years. Carbon-14 is stored in tree rings after about 30 years in the atmosphere, and so we can't see the solar cycle, but we can see the modulation of the solar cycle in carbon-14. So here's a beryllium-10 record from an ice core going back to 1440. So the amount of beryllium-10 production is anti-correlated with the sun's magnetic field. So when the sun's magnetic field goes down, you get more beryllium-10 production. And so this maximum you see here is the Maunder minimum. And then there are other minima. So Hannah liked a long record, so we can go back quite a long timescale here. There are other minima that occurred in the 15th century, and there's something called the medieval maximum as well. In fact, this record goes back for about 20,000 years. So I think it'd be worth going back and analysing some of this data, having seen Bruce's talk. Trying to work out a little bit more whether stochastic or deterministic models are better for understanding that data. Okay, I'm not going to say very much because there are definitely experts in the room, but if you're a dynamo theorist, you want to know about shears, and Hannah talked about this. So we've known for a long time that the sun's equator rotates faster than the poles. Essentially, the solar interior rotates as a solid body. There's a latitudinal differential rotation that occurs throughout the convection zone, and there's this layer of very strong shear at the base of the convection zone. Sometimes it's called the thin matching region, which is known as the tachocline at the base of the solar convection zone. It's just in the stable layer. We know that this surface differential rotation, which is maintained throughout the convection zone, is presumably kept its shape throughout the convection zone by convective processes. Whether it's Reynolds stresses in the convection zone or a so-called thermal wind is an interesting question, and the contributions of those to the particular form of the differential rotation is an interesting one. If the sun were a very rapid rotator, you might expect, of course, the contours of constant differential rotation to line up with the rotation axis, but they're tilted from that. They're essentially on conical sections. And so that's an interesting thing to try and understand. And numerical models are giving us some idea. I'll say a little bit about that later on, about where this comes from. But the primary thing we'd like to get right in our models is that the fact that the equator is rotating faster than the poles. Okay, that's the order one thing that you kind of get out of this. And we believe that other stars, the equator is rotating slower than the poles, and that's called an anti-solar differential rotation pattern. So a good question is, why does the sun have a solar type differential rotation pattern, whereas other stars don't? So I'll say a little bit about that. Okay, meridional flows. I didn't know it was settled, but I had a look at this paper. They don't seem to think it is settled, or he doesn't seem to think it is settled. So apparently this is the one that you should, and he's sat in the back. So you have to take this one as the right one. I have no idea, but you can see that the meridional flows There is some disagreement still about how they close, but one thing everybody agrees on is that it's towards the pole at the surface, and then there is some kind of return flow at the base of the convection zone. It could be one cell or two cells. There could be quite different shapes, I guess, to the meridional flow. But I think we're all agreed that we are all agreed that the meridional flow is poleward at the surface. And this, as Hannah said, is a vital component for some dynamo models. Some of the dynamo cartoons, this meridional flow is a vital component. And it may feed into other dynamo models as well, as we'll see, but perhaps it's not so vital for the actual generation process. I think from theory, it's important to note that we probably think that as stars spin faster, they tend to have slower meridional flows. And that's going to be important a bit later on when we're criticizing some of the models. Okay? So as stars spin faster, they tend to have slower meridional flows. That's not an observation, that's just from models. Okay, so what about other stars, solar type stars? I'm not really going to talk about non-solar type stars today. So we can look at the chromospheric calcium H and K emission, which is correlated with magnetic activity. And you see the sun is not alone in having cycles. If we viewed the sun as a star, this is what it would look like. So here's the sun's 11-year cycle. But you can see other solar type stars, they have cycles of about the same time period. Okay? Some of them seem to be going into minima, perhaps, but they definitely do have well-defined cycles. If you try and work out the cycle period against the rotation period, you can see that the cycle period tends to increase with the rotation period. Okay, so as the star spins slower, the cycle period. I'll get that the right way up. Let me get that the right way up. As the star spins faster, the cycle period shrinks. That's the way I think of it. So as the star spins slower, the cycle period goes up. Yeah, that's right. Good. Okay, so that's something we would like to understand to calibrate our dynamo theory. Can we get a dynamo? Hannah said it'd be nice. We'd like to explain the sun's magnetic field, but I think we'd like any dynamo theory we have to be able to just explain more than just the sun, perhaps to explain other solar type stars as well. We also know that as the star spins more rapidly, the amount of activity goes up as well. The field strength goes up. So these are two observations that we'd like our dynamo theory to be able to explain. Okay, so much for observations. Okay, I wasn't meant to talk about observations at all, but I thought I'd better have. So, basics for the sun. Well, we all know that the equations for the solar interior, at least, we know the equations. There's no argument over the equations. We have to solve a momentum equation, an induction equation, conservation of mass, some kind of energy equation, and we could have some kind of gas law relating pressure, density, and temperature. So this is the set of equations. So we're not having any argument about that, but what we can't do is solve them on a computer. I think it's fair to say we can't just put these on a computer and solve them. And the reason is because the parameters are so extreme, and all you geodynamo theorists are there going, yeah, of course we know the parameters are so extreme that we have the same problem. If I want you to take one thing from this talk, it's that the problems in solar and stellar dynamos is in a completely different place in the equation set than it is for the geodynamo. So from a dynamo theory point of view, it's interesting to compare and contrast. So this is if you're going to take one thing from this talk, this is it. And it's down to Chris Jones, 20 years ago in Caramulo in Portugal. He was trying to explain the difference, and he said, for the geodynamo, we are having problems getting close to the correct parameter regime in the momentum equation. Those guys, and at this point he kind of dismissively pointed at the solar physicists on the other side of the room, still can't solve the induction equation, okay? And absolutely right, and this is 2003, and we still can't solve the induction equation. So whereas you guys are trying to get your balances right and the momentum equation and all of this stuff, we really can't solve the induction equation, and it's just as true today as it was then. So why is this? Let me just have a look at some parameters here, and we'll try and just go through this slowly. So the magnetic Reynolds number in the sun is of this order. We can argue about factors of 10, but I think we're going to say it's pretty big. It's huge, okay? Whereas in the Earth, I think it's fair to say we can get this on a computer. We can simulate flows with RM of about 500 on a computer, even in 3 dimensions, quite happily. So this is impossible to reach in the solar regime. So we have to do something different. The Reynolds number is large. I think it's important to say that inertia and Reynolds stresses are important in the sun. Yeah. Both for the sun and the Earth, the magnetic Prandtl number is small. And this means that the dissipation scale of the velocity is much smaller than the magnetic field in both. That has different consequences, I think, for the two types of modelling, which I may say a little bit about. The Prandtl number is tiny in the sun. This is a big difference to the Earth. And this leads, or could lead, to very different dynamics of convection and instabilities in stable layers. So in a Prandtl number order 1 type situation, for example, shear instabilities are controlled by the Richardson number. Whereas in a low Prandtl number fluid, it's the combination Prandtl times Richardson number that's important. And there's a very nice review of the effects of Prandtl number, having a low Prandtl number in stellar environments by Pascal Garot. And this plays a big role in some of the so-called instabilities in stellar interiors called Goldreich-Schubert-Fricker instabilities. The Rossby number in the sun, we'll come back to this, somewhere between 0.1 and 1, whereas in the Earth it's tiny. So the Earth is much more rotationally constrained. You have these quasi-geostrophic dynamics or magnetostrophic balance on certain scales. Oh, can't spell. In the sun, the Reynolds stresses and thermal wind will be important. What's the ratio of the magnetic energy to the kinetic energy in the dynamo? Well, I think we'd be very happy if we could get a magnetic energy which was about the kinetic energy in a solar dynamo type calculation. Whereas, of course, in the Earth, it's huge. It may balance the Coriolis force. It may not quite get to that level, but it's certainly very much bigger than the kinetic energy, the magnetic energy. So those are some differences. And so, you know, what I think of as the primary problems for theory computation is for the geodynamo, you can't get the momentum equation to low enough Ekman number. And for the solar dynamo, I think we can't get the induction equation to high enough Rm. So what are the ways of tackling the problem? Well, perhaps in the geodynamo, you might like to choose a path in parameter space with a distinguished limit of the correct balances. What's the way of tackling the problem of not being able to get to high enough Rm? Well, we try and have a theory, mean field electrodynamics, or we do some theoretical investigation of turbulence models. The magnetic Prandtl number is too big in both. Perhaps you use different tools for the two. I won't say too much about that. As we heard this morning, reversals are very interesting in the Earth. A good question to ask is which nonlinearity causes reversals? And of course, for the solar dynamo, what sets the timescale for the reversal of the magnetic field? This 11-year reversal, 22-year magnetic cycle. Is it the meridional flow? Could be. Is it a turbulent timescale? It could also be that. Okay, so let's think about what we do for the sun. So because of the extreme nature of the parameters, there's no obvious way to proceed, okay? So modeling is typically taken one of these 3 forms, and I'll talk about the first 2. I'm not going to say anything about low-order models today, but usually there's been an awful lot of work on global computations. So what you do is you solve the relevant equations on a massively parallel machine. You either accept that you're in the wrong parameter regime, or claim that the parameters invoked are somehow representative of their turbulent values, or you may employ some kind of subgrid scale modeling. You could, and for years we have been, deriving mean field models. So you derive equations for the evolution of the mean magnetic field and perhaps the velocity field by parameterizing the effects of the small scale motions. So these are fairly unconstrained models. They can't do predictions because there's a lot of free parameters. And perhaps the role of the small scales can be investigated by employing local computational models. Low-order models are interesting, and I think they're very revealing. For low-order models could be based on symmetries, the symmetries of the equations, or the interactions. And you really just try to understand the basic properties of the systems of equations with reference to simpler systems. For example, if you wanted to know why the sun was sometimes hemispheric, or why lots of people are getting hemispheric dynamos in their very complicated 3D simulations, you could just go and read a paper by Jennings and Weiss, who talks about the symmetries in the mean field equations, and learn an awful lot from that. Okay, so let me go on to what people have done. And there are experts in the room who know an awful lot more about this than I do. But I think a prerequisite for getting the solar dynamo correct, if you're doing a computational model, should be to try and get the correct differential rotation. So remember I said the sun is rotating fast at the equator and slow at the poles. There is this, in the solar interior, it rotates essentially as a solid body. Why it does that, we don't know. It could be due to a magnetic field in the solar interior, which seems to me to be the most likely explanation. But there are questions as to why this tachocline, why this matching region is so thin. We'll hear talks about that, I think, later on in the week. So the question we have, and people I think are calling this the Convective Conundrum, is, why do our models, if we think they're at the kind of right parameter regime for the sun, why do they tend to get what we call anti-solar differential rotation? So why do they get, the leading order question is, why are they getting the equator to rotate slower than the poles rather than faster than the poles? So as I've said it here, if the Rossby number is too high in numerical simulations, we get an anti-solar rotation. We can rotate the computation a little bit faster and get solar type differential rotation. So we decrease the Rossby number, we do get a solar type differential, I say we, I don't, these guys do. It's the royal we, I guess. So we do get a solar light differential rotation. And so the question people have asked, and we were asking it a couple of weeks ago, is what acts to make the effective Rossby number lower than we thought it was? So that's an interesting question. I don't think we came to an answer a couple of weeks ago. We had three teams you could choose to be on. So why might rotation be more important than we think? Well, one argument is that actually all our estimates of the Rossby number come from mixing length theory. Mixing length theory has certain assumptions built in, and they may be wrong. Indeed, they may be wrong about the amplitude and the length scale of the convective flows. Well, the Rossby number depends on both the amplitude and the length scale. So this nice paper looks at how you might expect in a rotating system the Rossby number to change, not based on mixing length theory, but based on ideas from years and years and years of simulations of rotating convection. And what you see is that the dashed line is what we think should happen for a rotating system. You see that although the convective speed goes up, which you might think leads to an increase in the Rossby number, the length scale also changes such that the Rossby number is lower than we think, okay, lower than we thought. Okay, so that's one way out of the convective conundrum. We just heard about entropy rain. I don't have anything to say except non-local heat transport via entropy rain may make the flows a bit slower than we thought. If the flows are a bit slower than we thought, maybe the Rossby number is lower than we thought. So that's a possibility, again, for getting the solar-like differential rotation. Or it could be that the magnetic field plays a role, so that Maxwell stresses from a small-scale dynamo act to counteract the Reynolds stresses, and it's these Reynolds stresses that are leading to an anti-solar rotation profile. And so this is an idea, a very recent idea by Hotter et al., that if they get a sufficiently, I was going to say well resolved, but I don't mean that. What I mean is a sufficiently highly resolved calculation where their small scales go unstable to dynamo action, then they can get Maxwell stresses that counteract the Reynolds stresses and lead to and therefore you'd get a solar-like differential rotation pattern, whereas if you did the hydrodynamic case, you would get an anti-solar rotation profile. Okay. So imagine you've managed to get it all right in the sense that you've got the equator rotating faster than the poles. So imagine a calculation has managed to get a solar rather than an anti-solar differential rotation pattern. You remember, let me just go back here, the lines of constant rotation are tilted away from the vertical, from aligning with the rotation axis, what is it that causes this tilt? So that's the next thing you might like to try and understand. And then the bottom entropy boundary condition may play a role. Indeed, the distribution of entropy throughout your convective domain may play a role. So for a thermal wind driven by the interaction of latitudinal entropy gradients, temperature gradients, and rotation, so in a thermal wind, the departures from cylindrical symmetry are maintained by latitudinal entropy gradients, and these could be caused by the influence of rotation on the efficiency of convection, e.g. if the convection is more efficient at the poles than it is at the equator, then that would set up an entropy gradient in latitude, or this entropy gradient may also be set up in the tachocline, and there are models of both of these. Of course, the Reynolds stresses in the convection zone may also play a role in tilting the convection, tilting the differential rotation. And gosh, this is going back 20 years, Sasha. Well, there you go. He had dark hair, so did I when he did this, yeah. So you can have a look at the competition between these two. And at least this paper came to the conclusion that this thermal wind is more important in the lower convection zone, whereas the Reynolds stresses play more of a role in the upper convection zone. So there's competitions. Again, I have to stress that these are hydrodynamic calculations. We're still in the wrong parameter regime, but we haven't addressed the problem of solving the induction equation yet at completely the wrong parameters. So let's go to dynamos. And let's think about computational solar dynamo models. And there's a long history of this, I guess going back even further, nearly 50 years, 47 years, I guess. Going back to Peter Gilman and Gary Glatzmeyer, trying to look at computational models of spherical shell convection, either in the Boussinesque initially or the anelastic approximation. And in the early papers, amazingly, they found cyclic polarity reverses which depended on the differential rotation. Okay, and they speculated on this type of diagram. They talked about the influence of rotation on the dynamics and the electrical conductivity. They did this diagram as to whether you've got dynamos with cycles, dynamos without cycles. They're talking about whether convection drives differential rotation. If the differential rotation is strong enough, then you can get cycles, exactly as we would understand using mean field theory. There's now, I think it's fair to say, a large number of these models using a variety of codes and techniques. It's important to pass the anelastic benchmark if you're going to come up with your own code, but I think all of these do, so that's good. These are absolutely heroic calculations, though I want to stress they all have a magnetic Reynolds number of about 100, or 500, if we're depending on how we're measuring the magnetic Reynolds number. And recall that this means that the ohmic diffusion time is only about 100 times the convective time. The ohmic diffusion time in the sun is 10 to the 9 years, okay? And the cycle is on 11 years. Just trying to talk about the separation of scales. So the separation of time scales here is about 100. There it's whatever it was, 10 to the 8 or something. So I do not have time to summarize everything these computational solar dynamo models have found. These are based on, I think we would call these distributed dynamos. The dynamos being generated by the convection, so it's very, very different to what Hannah was talking about. But what do they find in general? They find that as the level of turbulence increases, the reversals become more chaotic over a shorter time scale. It's harder to build a large-scale component, but the bottom boundary conditions can play a role. You can get things going a bit better if you put a simplified tachocline in the model. Then you can get these more ordered type fields in the tachocline. So this is work of Matt and his collaborators. You get an ordered field within the tachocline, a disordered field within the convection zone. And this is reminiscent of what some people call an interface dynamo scenario. That's a cartoon. We only have cartoons. It's harder to get reversals, okay, in this type of situation. However, I think it's fair to say that magnetic cycles and ordered fields were found in later simulations using implicit large eddy simulations. They find it strongest at the interface between the convection and the radiative layer, but it was harder to find equatorial propagation of the field. However, if you go on in a spherical wedge calculation, some work by Petri Kapala and these collaborators, you can find cyclic reversals with equatorward propagation. So this is an example of the cycle period, I think, well, definitely being set by a turbulent timescale, not by a meridional flow, by a turbulent timescale. There's equatorward propagation. Stronger rotational constraints lead to more ordered fields. So you can have a look at Antoine's paper for more about this. And all of these are fairly well described by a mean field theory. And I think they're fairly well described by a mean field theory because RM is so low. Okay, we'll come back to that in a minute. As I said, caution, in these calculations, the ohmic time is not that different. So, well, that's not right. The ohmic time is the diffusive time. The ohmic time is not that different from the advective time, that should have said. And the saturation is on an ohmic time scale. And it's really not clear to me, at least, what sets the cycle period. Oof. Okay. So this is coming back to some of Hotter's work. So in some of these implicit large eddy simulations, as you increase the level, the resolution, the large-scale field, which emerges at low resolutions, disappears for moderate resolutions and comes back for high resolutions. And this has been interpreted as I'll come back, as a magnetically driven EMF. So somehow the small-scale magnetic fields they saturate and then they lead to an EMF on top of what you would have seen kinematically. And this is very reminiscent of some work that was done by John O'Squire and Amitava Bhattacharjee for the magnetic shear current effect. So this is interesting, but I'm never quite certain what to make of implicit large eddy simulations for dynamos. Okay, so I'm here to set the scene for the rest of the conference. That's what I was told. So these are some talks to look out for. So see Antoine Strugarek's talk for the latest on cyclic dynamos, is that right? And then there's Bonnie's talk on dynamos in stratified domains, Sasha's talk for the latest on tachocline dynamos, and Lauren is going to talk about why the tachocline is there. So if you're sat there wondering, I'd like to know a little bit more about any of those things, just hold your horses, they'll be coming. Right, I was thinking ages and ages whether to put this in, and I can't not put it in. but I'll go through it quite quickly. We can't do these things using computational models. We need a little bit of theory, and the theory that we have comes from what's called mean field electrodynamics. I'm going to only take you through it very quickly, and yeah, for those people who know it, you can have a sleep. For those people who don't know it, you can have a sleep. But it's in my contract, I have to do this. Okay, so imagine you take the induction equation and you choose an averaging procedure. So we can average over time, over space, and it helps, although it's not essential, if the procedure satisfies certain rules, it enables you to manipulate the equations. Well, if you then split up your velocity field and your magnetic field into a mean and a fluctuating part, you can derive an equation which looks like this. And the key term is this nonlinear term here, u cross b. I'm calling it nonlinear because I've assumed u has been solved for by the momentum equation, which itself depends on b. Formally, this is a linear equation in b, but this is a product term at least. So you expand out the product, and the key to everything is this. This is the mean of the fluctuating velocity interacting with the fluctuating magnetic field. So the key thing to understand is the so-called electromotive force, the turbulent electromotive force, u prime cross b prime. And Keith, in his book, said there is now a satisfactory body of theory for the determination of E. The reason for this comparative degree of success can be attributed to the linearity in B of the induction equation. There is no counterpart to the linearity in the dynamics of turbulence. So what Keith was alluding to there is, of course, if you take the momentum equation and you average it, you get a term that looks like u dot grad u averaged, and that's already nonlinear. And so you're in trouble. Here, this is linear. This is an equation that's linear in B. And so there's an awful lot of machinery that went along based on the fact that this can be determined by this satisfactory body of theory, which is quite right. And I'm not going to go into details, but you derive an equation for the fluctuation. There's a pain in the neck term, which I'm not going to go into, so-called, Keith called it the pain in the neck term. And the equation for the fluctuations is formally linear, though it's inhomogeneous in B bar, and so you pose a relationship that the EMF is some linear functional of the mean field, and then you derive the famous equation that links the EMF to the mean field involving the so-called alpha effect and the turbulent diffusivity. So this is mean field electrodynamics. The tensors are sometimes called transport coefficients. They're determined by the mean flow and the statistics of the turbulence, which of course in real life depends on the magnetic field via the momentum equation. I'm sure you're all aware, if not, you have to go and read Keith and Emmanuel's book. Alpha is a regenerative term, and beta is, if it's isotropic, is a diffusive term, though some components of this tensor can lead to growth of the field. But you don't have to make use of the linearity of E. Lots of people write down turbulence theories for just pure hydro turbulence. What happens if you do a similar thing for the combined system with the induction equation in? Well, you could just derive an evolution equation for E. Okay, you derive an evolution equation. Remember, E is u prime. Sorry, I've missed off the primes here because I copied this from Axel's paper. U prime cross B prime. You differentiate it, so you get a u dot cross B bar and a u cross B dot bar. And then you go away and you work out what these things are just by substituting into the equation. And you find that there's an evolution equation for E bar, which involves what are called double correlations, i.e. things that are quadratic in the perturbations, and triple correlations, i.e. things that are cubic. And at this point, you rapidly realize that this is never going to work, because if you write down an equation for the triple correlations, you get something involving the quartic correlations. And so what most people do is, or lots of people do, is they take these triple correlations and just put a simple prescription to relate it back to the EMF. If you want to do something more fancy, you have to read Nobumitsu's 110-page paper.
But 2020.
Oh, okay. 2020. Don't get the wrong 110-page paper. Whatever you. Okay. Okay, there's a problem, and the problem is called catastrophic quenching. All of that theory is for the kinematic problem, going back to the theory described by Keith, not the one I've just described. And I'm going to give this a physical explanation. The fundamental problem is that the alpha effect term that does the generating may get switched off at a very low level of the mean field. So rather than saturation, when the mean field comes into equipartition with the kinetic energy, which may look like this, and give you alpha and beta, these are reminiscent of some of the equations we saw this morning, I think. These are so-called quenching formula that says alpha switches off when the mean field becomes comparable with equipartition. It could be physically that saturation occurs, and it's more plausible when the fluctuating field comes into equipartition with the kinetic energy. And the problem is that the fluctuating field may depend on the mean field with a factor of Rm to some power in front. And if you put that into these formulae, okay, you see that, well, this thing is going to switch off if B0 squared is much smaller than equipartition. So as I've said here, this is very technical, and it's really linked to the timescale on which irreversibility is introduced into the system. I'm not going to go into any details. If molecular diffusion sets this timescale, then the mean field can only grow on an ohmic timescale. Some people try and get around this by having what are called helicity fluxes. If you can have these helicity fluxes on an advective timescale, so you can change the configuration of the field by getting helicity out of your domain, then you might be able to alleviate this field only growing on an ohmic timescale. I'm not going to go into any detail, but this feeds into why we're still drawing cartoons. Let me explain that. So some of these ideas can be tested in local domains, and if you want to have a look at essentially all of everything anybody's ever done, have a look at this paper by Axel, or this paper by Axel and Candu. So the local models allow you to test a higher level of turbulence and a higher magnetic Reynolds number than global models. And so people have done everything. They've used forced helical turbulence or convective turbulence. For forced turbulence in Cartesian boxes, they've done it with and without shear, with or without helicity fluxes through the boundary. They've done it with convective turbulence, with or without rotation, with or without shear, with or without, they've just done everything. They've done Boussinesq and elastic, fully compressible. And what they try and do is calculate these transport coefficients, the alpha effect and the beta effect. And they use various methods for calculating these. The most popular is the test field method by Schrinner et al., going back a long way. The least popular one is the one we came up with, just used by us. And in fact, not even used by us. What we call the modified Angstrom's method. But anyway, there's a lot of work done in trying to understand how these transport coefficients depend on Rm, on the presence of shear, on the presence of stratification. Okay, there's a whole other class of dynamo, which I'm not really going to have time to talk about. But these arise when the flow is driven by the action of a finite amplitude magnetic field. The others, the flow was driven by convection, by turbulence, and then that generated the magnetic field. You can have some types of dynamos where they're driven by a finite amplitude magnetic field. So these could be instabilities, so-called magnetorotational instabilities. You can have a look at some of these dynamos. Actually, these are done for accretion disks, but this kind of dynamo may be relevant in bits of the tachocline or may be relevant in the near-surface shear layer. There are these magnetic buoyancy-driven dynamos. We heard about magnetic buoyancy earlier. So this is one done by Kelly Klein, Nick Brummel, and Fausto Catania. Here, what happens is you have a shear flow which generates a magnetic field. The finite amplitude magnetic field goes unstable. It interacts with rotation, and that generates the alpha effect that you need to complete the dynamo loop. There are these Taylor-Sprout dynamos. These emerge from the instability, a current-driven instability in radiative interiors in the tachocline. And again, I'm setting up the rest of the conference. So there's going to be some talks and posters on these kind of dynamos, which are relevant for probably for radiative interiors. And the other type of essentially nonlinear dynamo is where the field breaks a constraint. So this should be familiar to all of you guys who know about the geodynamo for the strong field branch, and they may be relevant. This breaking of rapid rotation may be relevant to more rapidly rotating stars. Okay, so in the final bit of my talk, hopefully I've convinced you that we can't actually solve the equations computationally. Let me tell you about the cartoons people are drawing for dynamo action. And I think it falls into three main topics, okay? Three main types of dynamo. So there's the one which is called the distributed dynamo scenario. So here, the poloidal field, we've got all this cyclonic convection. We've got this convection in a rotating system. And so the poloidal field would be generated throughout the convection zone by the action of this cyclonic turbulence. The toroidal field is presumably generated by an omega effect. So if it's just happening in the convection zone, it's presumably generated by the latitudinal distribution of differential rotation. Possibly no role is envisaged for the tachocline, which is great because it'll then work for stars which don't have a tachocline. And angular momentum transport in this case would presumably be most effective by Reynolds and Maxwell stresses. The thermal wind would be important. So of course there are pros and cons, okay, to this scenario. The pros is, I don't know, this scenario is going to work wherever convection and rotation take place together, which is stars, okay, on the whole. The cons are that the computations show it is hard to get a large-scale field, at least if you're sufficiently turbulent and you're at sufficiently high RM. Also, mean field theory shows that it's hard to get a large-scale field, so-called catastrophic alpha quenching. I don't know if this last thing is true, whether buoyancy would remove the field before it can get too large, but there's a question as to even if you get these things working, can you keep the field in the dynamo region long enough to get the field strengths that are observed? But I would say, 90% of the computations are aimed at understanding these distributed dynamo scenarios. You can modify this dynamo slightly by taking into account the fact, I didn't say very much about it, the differential rotation shows us that there's a shear near the surface, the so-called near-surface shear layer. Okay, and perhaps it's this shear that plays a big role in the dynamo, not this shear at the base of the convection zone. Okay, so there is an idea of a near-surface dynamo scenario, which is essentially rotation and convection, which is modified by the near-surface shear. So the near-surface radial shear plays a key role. Question you have is, how does one of these dynamos, where the field is generated in the shear layer, how does it satisfy Joy's law? Well, perhaps it's just due to the rotation rate in the near-surface shear layer. So statistically, you might get something that looks a bit like Joy's law. These are calculations due to Axel. But it has the same pros and cons as the distributed dynamo. But it's possible that this shear could play a role, I guess. Okay, we heard about this flux transport dynamo scenario. And this seems to be the favored scenario of solar physicists. Not the favored scenario of dynamo theorists, but the favored scenario of solar physicists. And we heard about this. So what happens is the poloidal field is generated at the surface of the sun by the decay of active regions with a systematic tilt, so-called Babcock-Layton scenario that provides us with an alpha effect. This field is then transported towards the poles by the observed meridional flow. Okay? And then the flux is transported on a conveyor belt to the tachocline, where it is sheared into this field that you see, which then goes unstable, presumably via magnetic buoyancy, rises to the surface and completes the loop. So you have an alpha effect at the surface, and then you have a shear at the base of the convection zone, and then you have a meridional flow, which links the two. Okay? And Robert is going to talk about the pros and cons, probably more about the pros, I would guess, of this type of dynamo. So there are pros and cons that I think of. So the pros, there are definitely pros. It does not rely on the turbulent alpha effect in any way, shape, or form, which is good because we're having lots of problems with the turbulent alpha effect. And therefore, all the problems of alpha quenching, they're not a problem at all. A pro is that a sunspot field is intimately linked to the polar field immediately before. And this, if this model is right, may give you a way of predicting what the next solar cycle is going to do, because you just look at what the polar field was doing the cycle before, because that's the one which is going to get dragged down, sheared out, and provide you with the next cycle. What are the cons? Well, it requires a strong meridional flow. We've seen that there may be that strong meridional flow at the base of the convection zone of the right form. It ignores, I think it's fair to say, everything that happens between here and here. All the poloidal flux return to the tachocline via the convection. There's plenty of magnetic field, we think, which is generated here, which wants to rise up, but then gets pumped down by the convection. So it ignores that. That doesn't form part of the scenario. It may be that any effect of an alpha effect up here may be swamped by alpha effects if you could get them closer to the tachocline. It relies on the existence of sunspots, or at least flux at the surface, to work. So a question you have to ask is, what happened during the Maunder minimum when there was a nice cycle going through the convection zone, through the sun? And I think one thing that really is a problem for these models is that if you take these things and you run a model, is that the hemispheres rapidly decouple. So the northern hemisphere rapidly stops being in phase with the southern hemisphere. Now you can get around that, and I'll show you how you get around that. So these were all recognized as cons a little bit, a long time ago now. And so what people did was they recognized that there may be some tachocline instability, some instability in the tachocline, one of these dynamic instabilities, essentially nonlinear dynamos, which also provides an alpha effect. So you not only have the alpha effect at the surface, you have an alpha effect at the base of the convection zone. So as I said here, in addition to the poloidal flux generated at the surface, it's also generated due to an MHD instability. And this helps with two of the problems. So you get rid of two of the cons. It helps to couple the hemispheres. You have a more global field, and so the hemispheres no longer decouple. And it helps with the Maunder minimum problem, because you just argue that when this dynamo switches off because there's nothing happening here, you just rely on the one down here. Okay? So it helps with that. It can get you out of the Maunder minimum problem, or the global minimum problem. You still have the remaining cons, and maybe Robert's going to tell us how we get around these. But I think something that has to be faced by these kind of models is that from theory, you expect the meridional flow slows down as the rotation period increases. But we know that as the rotation increases, the cycle period decreases. So this is going the wrong way. So it may explain the sun. It doesn't explain any star like the sun. Doesn't sound very feasible to me. But, there's problems with all the other scenarios. Then there's the so-called interface or deep-seated dynamo problem. I'm not going to go through details, but this has a role for the tachocline. And it has a role for the tachocline because the tachocline is used to get round various of the problems with having just everything in the working in the convection zone. So in this case, the dynamo is thought to work at the interface of the convection zone and the tachocline. The mean toroidal field is created by the radial differential rotation, and it's stored in the tachocline. It might go unstable. We saw these like rising tubes from Hannah's talk. This is a cartoon by Nick Brummel, interacting with rotation. Some of the field, flux, may get pumped back down into the tachocline. The mean poloidal field is created by the turbulence somewhere at the base of the convection zone, or perhaps a dynamic alpha effect in the lower reaches of the convection zone. Dynamic alpha effect being what? Due to one of these instabilities. This scenario also has pros and cons, I'm afraid to say. So the pros are that the radial shear provides a natural mechanism for generating a strong toroidal field. The stable stratification in the tachocline enables the field to be stored and stretched to a large value. Okay, this is why Parker thought of this in the first place. Because you're storing the mean magnetic field away from the convection, where the alpha effect is taking place, the alpha effect is not suppressed, okay? Because you're storing the mean field here, and so, you know, the convection zone can get on with generating poloidal field. It's a very sensitive issue as to whether this actually works, but this is why Parker proposed it. The cons is it relies on, okay, here's doing all your generating, your alpha effect. We somehow need to get that poloidal flux down into the tachocline to get it to be sheared out. How is this achieved? There's a delicate balance between turbulent transport. The main problem with this is that, what are we doing? We're painting ourselves into a corner, aren't we? What about other stars with no tachocline? What do we do there? So that's a definite con for that scenario. Okay, it's been quite technical. So again, I'll do my advert. If you really want to know the technical details, especially about mean field theory, look in this book. If you want to know about the link to observations and what's going on, look at this paper. If you want something that's free, look at this paper. Okay, and just some further thoughts. If you're going to take one thing away, the problem for solar stellar dynamo models is that Rm is too small in the induction equation, okay? We're going to worry about the momentum equation when we've sorted out this problem here, okay? Oh, well, we still worry about it, but we can't get around this problem. Rm is too small. We have scenarios suggested for getting around the problem of this catastrophic quenching. None of them are entirely satisfactory. I wouldn't put my money on any of them. We need to know something about the role of the meridional flow. Meridional flow could be important in all of these scenarios, is definitely critical to one of those. And for the convective conundrum, it may help if the sun is at a lower Rossby number than we thought. Okay, thank you, I'll leave it there.
Okay, thank you very much, Steve, for a characteristically provocative talk, I would say.
I'm trying to be provocative.
So, Robert.
Oh dear, here we go.
And you're time limited.
Yeah. So I just want to make two comments. The first is you speak about the Babcock-Leighton and flux transport together, but the Babcock-Leighton is much older, does not rely on the tachocline, and these two families are somewhat distinct at least.
Yeah, I was just saying the Babcock-Leighton is just the mechanism for getting the alpha effect at the surface. If you want to then couple it to the tachocline, you need the meridional flow. And that's where the flux transport comes in.
Yeah, and so I'm certainly not arguing it's coupled to the tachocline, so I won't be discussing it at all.
So some people just believe in Babcock-Leighton on its own. Okay.
Yes.
Yeah.
Okay. And the second point is this period-period relationship. I think that diagram has changed quite a bit in the recent years. We're more filling in, and it's difficult to even say. So for the activity, for the ones where you have the inactive and active stars together, there's stars which are on both branches of those, and so it's difficult to know which branch of those dynamos corresponds to what happens on the sun and what happens to other stars.
Yeah, okay, so what Robert's saying is that, and he's right, he's exactly right. Hang on, sorry, I'll find this. this one. You're saying this diagram is filled in. Yeah, I agree. It has filled in a little bit. But I don't see anything that's going the other way.
So in the Jeffers paper, Jeffers government et al., he argues that the dynamo on the inactive branch actually corresponds to the solid dynamo, corresponds to the active branch.
Yeah, I know you do. Yeah. Okay, this is filled in. Yeah. I'm not going to say anymore. You're right, Robert. Yeah.
Okay. More questions? You've intimidated everyone, Steve. I think.
I doubt it.
Not quite.
Yeah.
As you know, we have been discussing that quite a lot with you and Fausto for many years. My problem with the catastrophic quenching that you are deducing that from Cartesian box simulation often. And it's what we find in the global simulation, that what comes first is the omega quenching. We see the differential rotation being quenched first before we actually see the energy in the convection being modified significantly. Yeah. So the first thing we see is the energy in the differential rotation being, modified and feel the Lorentz force or Maxwell stresses. And so my problem with the catastrophic quenching on the alpha effect that need the interface dynamo is not that it doesn't exist. I'm not saying it doesn't. But what we see in the global simulation, that it comes second after you have first quenched the differential rotation. And what we were able to see more recently, and that's a discussion we have with Petri and Jorn and few others and Axel, what we see in some of this simulation now is that actually this feedback of the Lorentz force on the differential rotation can lead to a local reversal of the differential rotation of the shear that you mentioned, and that can trigger a cycle. And what we find in the latest simulation, that actually the Parker-Yoshimura rule may be working for the short cycle simulation, the one that have a cycle of 1 or 2 years. But for the long, decadal long, like the sun dynamo, we need to have this kind of, I call it nonlinear, but like Alexandre Fournier already told me several times, but your convection dynamo are already nonlinear. But what we meant by nonlinear meant that if we don't have the feedback of the differential rotation, you don't actually get the cycle. You see? Okay. So there is some subtleties there. You know?
Oh, well, yes, there are some subtleties. So I just want to say, I mean, the omega effect is definitely affected by magnetic field. So this is what you mean by omega quenching. The problem is that the alpha effect is incredibly sensitive. It's incredibly subtle. And I just want to point out that what you see in global simulations is at RM of 10 to the 2 or 10 to the 3. And what's being argued about for catastrophic quenching is at RM very, very large. And so what you see at RM 10 to the 2, 10 to the 3 may not be right. And really, there's an awful lot of theory that goes behind catastrophic quenching that says at high RM, you really have to get around that problem. I mean, be it by helicity fluxes, be it by something else. I'm not saying differential, some people call it lambda quenching, omega quenching, all of those things are not important. They may be important. But really, this is the generative term in the induction equation. And so we really need that to work at high RM.
Well, Team Biscuits will wait, but we've got time for one more, David.
Well, just following on from what Sasha says, I mean, there were lots of problems with alpha quenching. There were serious effects, serious problems even with a mean field picture before we start arguing about the alpha suppression. I mean, the picture that Steve put up there, you have the whole argument actually relies on the fact that the fluctuating field decays in the absence of a mean field. That's behind the whole of mean field theory, and that's not true, of course, because there's a fast dynamo, there's a small-scale fast dynamo, and that is also a major problem before we even argue about alpha suppression, which is a major problem.
Yeah, so what David is saying is that, there are terms here which have been, thrown away, which we know are there, because of fast dynamo theory. So it's linearly, though, inhomogeneously related to B bar. And that does cause problems for the theory, or could.
It may be true that the small Reynolds number we have in the simulation kind of blur this picture, which is much clearer in the asymptotic regime, which I agree. That's that we cannot deny or accept.
Absolutely.
I agree, but we do see dynamos that are building large-scale fields. Yeah. And still being, some quenching of the omega effect or lambda effect, as you want, and still some convection going on. So you are able to maintain. So we don't see the same link, and I think that comes in part through some geometry effect that we tend in a global simulation to have the dipole and or the quadrupole, and we see this interplay between the two dynamo family. I have the impression in the Cartesian box, the way the flux is being considered may be a bit different. There is some geometrical effect, I think, between the two that are not trivial to take into account.
Did you want to comment, Steve? Or?
Well, John, it is interesting. I think we had some discussion about why the spherical shell is different to Cartesian layers in terms of building large-scale fields, not just for turbulent dynamos, but for kind of Earth-like dynamos as well. I think that's an interesting question.
Okay. Last chance for questions? One at the back. Okay.
Yes, so you mentioned this work by Hota, recent work, saying that strong magnetic field comes back when you increase turbulence even more. So isn't that problem solved?
Oh.
Not that one.
Yeah,
yes,
it was.
Maybe that one.
It was there, it kind of went away and it came back. Is that the one you mean, Nathaniel?
Yes.
Okay. It's problem solved if you believe implicit large eddy simulations. It's one where you let the numerical noise do your dissipation for you. It's a fancy term for let your errors do your dissipation. I want to say one thing. In the induction equation, there's only two terms which lead to evolution of the field. There's U cross B, curl of U cross B, and there's eta del squared B. If you've got eta del squared B wrong, you've got it wrong. Now, you may want to use hyperdiffusions and things like that in the momentum equation. There are other things that can balance, lots of things. But in a dynamo calculation, you've only got those two, and if you get one of them wrong, I don't quite know what to make of it.
And I think Robert wants the last word.
Oh.
I just want to check. So you mean this works provided the next simulation doesn't change completely differently?
Yeah.
Yeah.
Okay.
Well, I mean, if we just had these two, you'd have said, okay, well, you'd have said job not done, right? But now it's job done, and who knows what happens, whether job's done or not. T's done, though, I think.
The convergence is a real issue in the simulation of EGUT, and we have talked about it in Bern, as you know. So that's really, I agree with you, Steve, that's really the key. Hyperdiffusivity has been shown to be wrong in weather forecasting, in other people are doing weather. That's why Smagorinsky was invented and many more.
But it's got more chance of working there. I mean, in the induction equation, there's two terms, right? In the momentum equation, there's lots of terms, and other ones can balance if this one's a lot smaller. I'm happy with that. I'm happy with it. Well, reasonably happy.
Okay, perhaps we should draw it to a close. Room for discussion outside with the tea and coffee. Thanks so much. So can we thank Steve one last time?